Let's work practice problem number 6 on page 255 in chapter 11. I'll read the problem. It's right here. Number 6, it says, a 90-kilogram rock climber first climbs 45 meters up to the top of a quarry, then descends 85 meters from the top to the bottom of the quarry. If the initial height is the reference level, find the potential energy of the system involving the climber plus the earth at the top and the bottom, and draw bar graphs for both situations. I'm not going to worry about the bar graph here, but so let's go ahead and solve it. I've sketched it out here with given, find, and solve. It says, so here's my cliff, the cliff of insanity. All right, and here is our climber. But they actually start from here. I don't know why. They just did that to make the problem harder, I guess. But you start here. Here's your 90-kilogram climber. That's a pretty big dude. And then up we go. We climb 45 meters to the top. We want to know what is our potential energy at the top. And then they climb down to the very bottom. What's their gravitational potential energy at the bottom if we use where they started originally as our reference, where we measure our height from. So let's solve. So the potential energy at the top is equal to mgh. Now this is the work. Now, mg, that's the force of gravity. And then the height, that's our height above the reference. And so, well, we have 90 kilograms. And then G is 9.8 newtons per kilogram. Now, here's what somebody did. She put a negative right here in the 9.8 because they think, okay, gravity is down. But remember, when you're calculating work, you want the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. And so you don't really need to make this negative here. This G is just m times G. That's the magnitude of the force of gravity. And then our height above that reference is 45 meters. And notice the kilogram cancels. We get a newton times a meter is a joule. So this works in terms of units. So let's go 90 times 9.8 times 45. And I get 3.96 or 3.97 actually times 10 to the 4 joules, or you can say, 39,700 if you're rounding it off, and you should round it off joules. Either way is all right. This is one of those numbers that's like, do you use scientific notation or not? It's kind of up to you. But, this isn't much harder to write down than this. All right, and then, so now at the bottom, it's just mgh again. But what is our height at the bottom? See, our height is measured from here, but we're below that height. So we have a negative height. And what is that height? Well, if from here to here is 85, and here it is 45, we're 85 meters below the top, but we had to climb 45 meters to get to the top. So it's going to be 90 kilograms times 9.8 newtons per kilogram. But what is our height? Our height, well, it turns out to be negative 40, right? But how do you get that? Well, it's 0. Oh, I'm sorry. It's 45 minus 85. And so this turns out to be negative 40. I mean, if from here to here is 85, but we start 45 meters up, that means it's 40 meters above the bottom of the cliff. So that's negative 40 meters. And so the potential energy at the bottom is equal to 90 times 9.8 times negative 40. Negative 3.53 times 10 to the 4 joules. Now, another way of thinking about this, what this means right here is that if your reference was at the bottom, this is how much you would have to do this much work just to get to that 40 meters up. So, and then you would do this much more to get all the way to the top. So, gravitational potential energy, you got to pay attention to where you measure it from. And you can have a negative height. You can be below your reference, and so you have negative gravitational potential energy. You can't do that with kinetic energy. There's no such thing as negative kinetic energy because it's 1/2 mv squared. So because the velocity gets squared, there's no way to have a negative quantity for that. Any questions on problem number 6? Very good. That is all.